Welcome back to the AI Frontiers podcast. Today, we're diving deep into a groundbreaking paper that explores a novel approach to learning weights in deep neural networks, hypernetworks. Joining us is Dr. Researcher's Name, the lead researcher on this paper. Thank you for being here.
It's a pleasure to be here. I'm excited to discuss this research with you and your listeners.
And we're also joined by Dr. Field's Name, a leading expert in the field of deep learning. Dr. Name, welcome to the show.
Thank you for having me. It's great to be here.
Let's start by setting the stage. Can you explain the core concept of hypernetworks in a way that even those unfamiliar with the technical jargon can understand?
Sure. Imagine you have a regular neural network, which we'll call the main network. It's like a machine that learns to perform a task, like recognizing images or translating languages. Now, instead of directly learning all the individual connections within the main network, what if we had a separate network that learned how to generate those connections? This separate network is the hypernetwork.
So the hypernetwork is essentially a network that learns to learn?
Exactly. It's a meta-network that learns the structure of another network. Think of it like a blueprint or a genetic code that determines the final structure of the main network.
That's a great analogy, Doctor. It almost makes it sound like the hypernetwork is a genotype and the main network is the phenotype. That's how things work in nature, right? The genetic code determines the organism's physical characteristics.
That's a very insightful observation, Dr. Parker. You've hit on one of the main inspirations behind this research. It's like the hypernetwork is the blueprint or the genotype, and the main network is the final product or the phenotype. It's a way to abstract the process of learning weights in neural networks.
Dr. Researcher's Name, you mentioned that hypernetworks can be used for both convolutional and recurrent networks. Can you elaborate on how they function differently in each case?
Yes, there are two primary types of hypernetworks discussed in the paper. First, we have static hypernetworks, which are used for deep convolutional networks. In these networks, the hypernetwork generates weights that remain fixed across time steps. The hypernetwork receives an embedding vector that represents the structure of weights for a specific layer in the main network, and then it outputs the weights for that layer.
And what about the dynamic hypernetworks?
Dynamic hypernetworks are used for recurrent networks, where the weights can change over time. The hypernetwork receives inputs like the current input to the recurrent network and the previous hidden state. Based on this information, it generates a new set of weights at each time step. So the weights adapt dynamically to the input sequence.
That's fascinating. It's almost like the hypernetwork is learning to adjust the weights of the main network on the fly based on the information it's receiving.
Precisely. This is one of the key advantages of dynamic hypernetworks. They can learn to adapt their behavior based on the specific input sequence, making them particularly well suited for tasks involving time series data or sequential information.
This is a really interesting departure from the traditional approaches to weight sharing in recurrent networks. Could you elaborate on the limitations of those methods and how hypernetworks address them?
Great question, Doctor. Traditional recurrent networks, like LSTMs, rely on weight sharing, where the same weights are used across all time steps. This can be limiting because it makes the network less flexible in adapting to different parts of a sequence. Imagine trying to translate a long text. Different parts of the text might require slightly different weight structures. Weight sharing prevents the network from adjusting its behavior based on context.
So hypernetworks provide a more flexible alternative to weight sharing.
That's right. They offer a kind of relaxed weight sharing, where the weights can be adjusted based on the context of the input sequence. This allows for greater expressiveness and adaptation capabilities. It's like having a network that can learn to learn based on the specific input it receives.
Can you shed more light on the specific techniques used for generating weights in the hypernetworks? How are embedding vectors used, and what are some of the key design choices for the hypernetwork architecture itself?
Sure. The key to generating weights in hypernetworks is the use of embedding vectors. These vectors are like compressed representations of the weight structure for a particular layer in the main network. The hypernetwork receives these embedding vectors as input and uses them to generate the actual weight matrices. It's like using a code to specify the structure of the weights, rather than directly learning each individual connection.
That's a very elegant solution. It allows the hypernetwork to learn a more compact representation of the weight structure, which can be significantly more efficient than learning each connection individually.
Exactly. And the hypernetwork itself can be designed with various architectures. In our paper, we primarily use a simple two-layer linear network for static hypernetworks. For dynamic hypernetworks, we use a smaller recurrent network, like a hyper-LSTM, to generate the embedding vectors dynamically. The key is that the hypernetwork architecture should be designed to efficiently learn the weight generation process, while also being flexible enough to represent the desired weight structures.
Doctor, this is fascinating, but can you elaborate on how you actually train these hypernetworks? How do you ensure that the hypernetwork learns to generate weights that result in good performance for the main network?
That's a great point. One of the key innovations in our paper is that we train the hypernetwork end-to-end with the main network using backpropagation and gradient descent. This means that the hypernetwork learns to generate weights that improve the performance of the main network on the task at hand. It's like a collaborative learning process where the hypernetwork and the main network work together to achieve the best results.
That's brilliant. So, you're not just training the hypernetwork separately to generate weights, but you're actually training it in conjunction with the main network to optimize the overall performance.
That's right. This end-to-end training approach is crucial for ensuring that the hypernetwork learns to generate effective weight structures that contribute to the main network's performance. It's like the hypernetwork is being trained to be a good architect for the main network, learning to design the right connections to achieve the desired outcome.
Let's delve into the experimental results. What tasks did you evaluate your hypernetworks on? And what kind of performance did you observe compared to traditional methods?
We conducted a comprehensive set of experiments to evaluate the performance of hypernetworks on various tasks. We used static hypernetworks for image recognition on the MNIST and CIFAR-10 datasets. For recurrent networks, we focused on the hyper-LSTM architecture, which we evaluated on tasks like character-level language modeling using the Penn Treebank and Hutter Prize Wikipedia datasets, handwriting generation using the IM online handwriting database, and neural machine translation using the WMT14 and FR dataset.
And what were the key findings? Did hypernetworks show significant improvements over existing methods?
The results were very encouraging. On image recognition tasks, hypernetworks achieved performance comparable to conventional convolutional networks, but with a significantly reduced number of parameters. This is a huge advantage as it can lead to faster training and deployment times.
That's impressive. So you're essentially getting comparable accuracy with fewer connections, which is a significant efficiency gain.
Exactly. And for recurrent networks, the hyper-LSTM architecture showed particularly promising results. On language modeling tasks, it achieved near state-of-the-art performance on both the Penn Treebank and NWIC-8 datasets. It also outperformed traditional LSTM configurations and achieved comparable results to layer normalization methods, which are commonly used for improving gradient flow in recurrent networks.
So, hyper-LSTM is not only efficient, but also achieves cutting-edge performance on these challenging tasks.
That's right. And we also saw impressive results on handwriting generation and neural machine translation. In both cases, hyper-LSTM achieved competitive performance compared to the best models available at the time. This shows that hypernetworks can be successfully applied to a wide range of tasks involving sequential data.
That's truly remarkable. Dr. Haram, what are your thoughts on these findings? How do you see these results fitting into the broader landscape of deep learning research?
This research is incredibly exciting and has the potential to reshape how we design and train deep learning models. The results clearly demonstrate the advantages of hypernetworks in terms of efficiency, flexibility, and performance. They show that we can move beyond the traditional paradigm of weight sharing and explore more sophisticated methods for learning weight structures in deep neural networks.
You're right, Doctor. This is a paradigm shift in how we think about weight learning in deep networks. It opens up new possibilities for designing more expressive and adaptable architectures. What do you think are the most impactful implications of this research for the future of deep learning?
I think this research could lead to a significant shift towards more compact and efficient models, particularly for tasks involving sequential data. It could also enable us to build more expressive recurrent networks that can adapt their behavior dynamically based on the input sequence. And who knows, it might even pave the way for developing completely new architectures and learning paradigms.
Doctor, did you encounter any limitations or challenges during your research? Are there any specific aspects that could be further improved or explored?
Of course. One limitation we observed is that hypernetworks might not always be ideal for tasks where different layers require significantly different types of filters. Enforcing a degree of commonality through the hypernetwork could potentially limit the model's ability to learn optimal filters for each layer.
That's an important point. So it seems that hypernetworks might be most suitable for tasks where the weight structure across layers is somewhat similar.
Yes, that's a good way to put it. We also explored the limitations of virtual coordinate-based hypernetworks, as used in previous work like hypernet. We found that these methods might not be as effective for practical tasks like image recognition and language modeling, suggesting that the embedding vector approach we used in our paper is more suitable for general applications.
So it seems that embedding vectors offer a more powerful and flexible way to represent the weight structure in hypernetworks.
Absolutely. And there are several other avenues for future research. We could explore the use of hypernetworks in other deep learning architectures like generative adversarial networks, GANs, and graph neural networks. We could also investigate different weight generation mechanisms within hypernetworks, including nonlinear functions and more complex architectures. And it would be interesting to develop more efficient and scalable implementations, particularly for large-scale models.
Doctor, do you have any thoughts on the potential applications of this research beyond the specific tasks explored in the paper?
The potential applications are vast and exciting. This research could revolutionize natural language processing, machine translation, text generation, image recognition, object detection, image generation, handwriting recognition, robotics, control systems, drug discovery, materials science, and even financial modeling. The possibilities are truly endless.
It's amazing to see how this research can have such a broad impact across so many different fields. To conclude our conversation, could you summarize the main insights from your work?
Our research demonstrates that hypernetworks, a novel approach to weight generation, offer a powerful and efficient alternative to traditional weight-sharing methods in deep neural networks. Hypernetworks can achieve competitive or even better performance than state-of-the-art models on various tasks, while also reducing the number of learnable parameters. They provide a flexible and efficient way to learn weights in complex models, especially when dealing with large numbers of parameters. This research opens up new possibilities for designing more expressive and adaptable architectures in deep learning, and has the potential to revolutionize how we think about weight learning in neural networks.
Thank you both for sharing your insights and expertise with our listeners. This discussion has been truly enlightening. It's clear that hypernetworks are a game changer in deep learning, and we're excited to see how this research continues to evolve and impact the field.